welcome back to our lab 8. So we just looked at the data and it does look like stereotype threat is powerful enough to have this acute effect. So I can only imagine what that does if it's happening all the time in people's lives. Can you imagine this? This is just a made up thing with white males that were in a career in which they trusted their mathematical skills and abilities, and it sufficed to put them in a group and just tell them, we're trying to figure out why Asians do better at this than white males. That was sufficient to lower the performance of that group. At least, we didn't run the hypothesis test yet, but that showed reduced performance. Let's see if that was reliable though. Because again, this is real data. Now that we've done all of our preparation, we're now ready to perform the test. We will again do so using the t-test function. In this case, the experimental question warrants an independent t-test. Please correct yours, independent t-test. So the null hypothesis is that we have the mean for the control group is equal to the mean of the threat group, and the alternative hypothesis is that they are different from each other. The general code for the independent t-test is here. We have the DVIV thing going on just like before. We have the name of the data set. We need to tell which kind of test that we want, two-tailed, and if it's one-tailed, if we want less than or greater than, what side of the curve do you want R to look at? You need to tell R if you want a paired t-test or a independent t-test. If it's independent, you set that to F. And when it's independent t-test, you need to come up with this parameter here and say that whether you can assume equal variance. And in this case, the Levene test told us, yes, you can, because P was greater than 0.05, so we can assume, so we'll put true. And we need to set up our confidence interval. And because it's a two-sided test, we have rejection areas for distributed on the two sides, 0.25 here, 0.25 there. So we want the boundaries of those rejection areas. And those boundaries are consistent with a 95% confidence interval. So let's play this up. So score, that's the DV. Group, that's the IV. The data frame is ST. I want a two-sided. Do not want a paired t-test. I want an independent t-test. Variance equal true. And we want a 95 confidence interval. And we can see that the p-value suggests that observing this particular difference between control group and threat group is unlikely if we were sampling, if stereotype threat had no difference, right? So not likely to observe this if stereotype threat has no difference. So we are rejecting the null. And the confidence interval confirms that because there is a change in performance expected with 95% confidence between 0.36 in that test score all the way up to 6 points. Interpretation results provide evidence that stereotype threat can lower the performance on a math test, even of a group that is not under such threat, under typical real-life situations. In particular, males that were exposed to artificial stereotype threat demonstrated significantly lower performance than those under typical conditions. The probability of observing the average difference of about 3 points or larger is about 0.02, so very low probability under the null hypothesis, right? It's about 0.02 if the threat had no effect. If we assume, right, no effect of stereotype threat. So if we expected no effect, it would not be very likely to find this difference. So the average difference can be expected between 0.36, kind of a small change, up to about 6 points, which in this test, given the scale of what people scored, is not negligible at all, with 95% confidence. So larger sample size would be required to get a more precise estimate of the size of the effect. Now, what if variances were not equal? Well, the only thing that you would do is just say F here, and when you run, you'll see that the degrees of freedom are a bit corrected here compared to here. It's pretty close. The correction didn't change much, and part of the reason is because it doesn't need to, because the difference is so small that it didn't need to change much. But it does affect the p-value a little bit because the t is the same, but because degrees of freedom change, then that will impact which t distribution you're looking at, and hence the p-value. But everything else is basically the same. All right? So this is asking R to do a Welsh correction. Okay, before you go, let me go with you to the independent activity for a minute, because I want to say a couple of words about that. So I'm giving you a real kind of complex data set, which is a data set from North Carolina. It's a state North Carolina data set with information on births recorded in that state. It was released in 2004. So you need to stop for a minute before you move on to do the rest of the activity and understand what each variable is called. So F age, for example, is father's age in years. Mage is mother's age in years. So it's a data set. If you load it here, sorry. Oh, it's good. I saw this. Record. Let me do this. Okay, here it is. And see, it's right there. So I'm opening it up, and each line refers to a birth. And you have the father's age. Maybe you don't know. Maybe they didn't know. Mother's age, 13. Mature, whether it's a younger mom, like a kind of a categorical variable, whether it's a younger mom or an older mom. The weeks, I forget. Let's go back there. What's weeks? Weeks is length of pregnancy in weeks. Preemie, whether the birth was classified as premature, preemie, or full term, so on and so forth. And then I will have you explore the data set a little bit, clean the data set a little bit, and then I'll have a problem for you to solve. And here in this problem that I created for you, I'm telling you that researchers were interested in whether there is a relationship between mother's smoking habit and the weight of the baby. So I wanted to know whether the weight of the baby is different between mothers that smoked during pregnancy and mothers that did not smoke during pregnancy. So I have a response variable, which is weight. It's a numerical variable. And I have an explanatory variable, which is the smoking habit. And then you're going to have to choose the test. You're going to talk about the assumptions, if you're meeting the assumptions or not, so adjust this accordingly. And then provide the code where you check these assumptions, right? And oops, this I need to delete. You need to bring it here. And then you provide the appropriate descriptive statistic, get the appropriate table by group, and then create your bar plot, or if you prefer, test out the line plot by group. And then you run your inferential statistics. You're going to set up your hypothesis. You're going to run the appropriate t-test, and you're going to do your decision and your interpretation, right? Interpret the results. Now for problem 2, and note that 85% of your grade will be for problem 1. But I want to set out a different challenge that you didn't experience before, so that will be only 15% of your grade. But what you are going to do is to explore a problem that you want with this data set. You're going to pick a pair of variables from the NC complete data set. And you're going to pick one numerical variable, one dependent variable, one response variable, and one categorical or factor, an explanatory or independent variable. So one response and one independent with 2 levels. And you're going to come up with a research question evaluating the relationship between these 2 variables. And you're going to formulate a question that can be answered with a t-test. Okay? And answer your question following the steps laid out in class for the appropriate t-test to be run. Oh my gosh, which kind of question? Whatever question that you want. So if we want to look at the data set here, you could ask things like whether full term versus preemie births differ in terms of weight gained or weight or the weeks. Of course, they will differ in terms of weeks. In terms of visits to the hospital. So you can pick a numerical variable. So we have visits, we have gained weight, and we have weight, and we have the age of the mother, the age of the father, and then you have categorical variables. How mature the mom was. Is that a very young mom? Was that an adult mom? So what are the levels here? Let's see. Mature. We have the maturity status of the mom. So mature or young. Does that make a difference in terms of the weight that the baby is born with? Does that make a difference in terms of what's visits? The number of hospital visits during pregnancy. So you can ask the question that you want, but you have the explanatory variable needs to be a categorical variable with 2 levels, and the variable, the response variable needs to be a numerical variable that you'll be able to compute means of. All right. So that's your task, and that will be 15% of your grade. And I have set out, the steps in the R&D that you have to create. All right, so that will be 15% only, but I want you to explore this because it is so important to learn how to formulate questions, and that can be actually answered with data. So I really believe that picking your own variables, coming up with a research question, and analyzing data to answer the question you came up with is basically what an innovative thinker in any field does. So I want you to practice that skill. Okay? It's just a skill that you can learn. All right? I will talk to you Wednesday if you come. If not, please get in contact if bugs are up and I haven't noticed them. Please do contact us to figure this out. All right? I'll see you then. Bye-bye.